Welcome to lecture number 7. Today we will talk about the two remaining ideal basic circuit elements, the capacitor and the inductor. And in the end of this lecture we will have a look at transient effects that has something to do with charging and decharging those elements. We already know from the first lecture that there are only 3 passive basic circuit elements, and those are the resistor we already used and the capacitor and the inductor. On this sheet you see the element equations for all 3 of them, and the element equations of the capacitor and the inductor will be the topic of this lecture. Let's start with a capacitor. A capacitor is an element where we have 2 metal plates which are isolated from each other. So a capacitor should behave like an open circuit. Okay, let's have a look at a computer simulation to see what happens at the capacitor. I built a small circuit in a simulation program. We have here an ideal DC voltage source. The voltage drop is 5 volts. Then here is a switch we could close or open, and then here are 2 resistors with resistor values of 1 kilo ohm each, and here is a capacitor. And as I said, a capacitor consists out of 2 isolated plates. This means this here should behave like an open circuit. Okay, what happens if we close the switch? We would have these 5 volts directly here at the resistor R1. And if the capacitor behaves like an open circuit, there will no current flow be here, and that means that we have no voltage drop here, and that would mean that according to Kirchhoff's voltage law we should have the full 5 volt from this resistor also at the capacitor. This here is just an oscilloscope and it measures the voltage at the capacitor, and we see the result here. Okay, I will start the simulation. You see here we have 0 voltage at the capacitor. Don't wonder, the switch is still open, so no source is connected to our circuit. Okay, and now I close the switch. And maybe the voltage drop at the capacitor rapidly jumps to the value of 5 volts. That would be if it behaves like an open circuit. Okay, I close the switch and okay, the voltage at the capacitor is increasing, but you see it takes some time until he reaches its final value. Let's disconnect the source and let's see what happens then. Okay, the voltage at the capacitor decreases, but again it takes some time until it reaches the final value of 0 volt. What happens there? Okay, we have seen that at a capacitor the voltage drop can't change its value rapidly. But why? Let's have a look in detail. Okay, we have our 2 isolated plates here, and now a current should flow. Okay, and if a current flows here, that means that a positive charge goes to the upper plate and a negative charge remains on the lower plate because a positive charge would leave it. And this leads to a voltage drop at the capacitor. And now the current remains flowing and there will be another charge on the capacitor, and that will lead to a bigger voltage drop here. I indicated by a thicker line for the voltage arrow. Okay, and still the current is flowing, and therefore there will be another charge and there will be a bigger voltage drop. And this goes on and on. And what you see here is that you need more charges for a higher voltage drop. And this is the reason why the value of the voltage can't change rapidly, because to change the voltage we need charges to flow into the capacitor. Okay, let's stop here and say we have this charge here on our plates. And the definition for the capacity is the amount of charge divided by the voltage drop at the capacitor at this charge. And we can solve this equation for the charge, and then it looks like this. And what we do now is we derive this equation by the time. This leads to this. The capacitance is constant, but we could take the derivation of the amount of charges and of the voltage. And do you remember the amount of charges derived by the time? This is a definition of the current. And therefore we found the element equation of the capacitor. It looks like this. And it means that if we have a variation of the voltage of the capacitor, then a current has to flow. And other way around, if the current is zero, that means that the derivation of the voltage is zero, and that means that the voltage is constant. Let's have a look what this means for a DC circuit in steady state. Steady state means that this charging or the decharging process is finished. So we don't have any variation of voltages or currents in time in the circuit anymore. Everything is constant. Okay, so our voltage at the capacitor is constant. And now we use our element equation. And we know that the voltage is constant, and therefore we know the derivation by the time would be zero. And we said it before at the element equation, when the voltage is constant, then the current is zero. So that means in a steady state DC circuit is no current flow at the capacitor, and that means it behaves like an open circuit. Let's have a look what happens at a capacitor if we have a sinusoidal voltage added. Okay, we can calculate the current just using our element equation. And this time our voltage is sinusoidal. That means it has an amplitude and the shape looks like a sine function. Okay, and if we take the derivation of this, then it leads to a cosinus function. And a cosinus function could be written as a sine function. You know, they look quite similar. We just have a phase shift between them. And therefore we could rewrite this equation like this. Okay, and that means we found the amplitude of our current. And if we compare our current and our voltage drop, we see that they are both sinusoidal, and we have a phase shift of 90 degrees between them, and the current is leading. let's have a look at another simulation. I built up a circuit here, and we have here an AC voltage source. I can display the voltage. You see here it's a sinusoidal voltage. The amplitude is 1 volt and the frequency is 100 Hertz. Okay, and then I built a small circuit here with 2 resistors and a capacitor. And now I want to see how the voltage at the capacitor looks like. So here in blue you see the voltage at the capacitor. And now I want to see the current through the capacitor. Okay, it's the red curve. I'll take out the input voltage and now let's just compare. In blue we have the voltage at the capacitor and in red we have the current. And you see they are both sinusoidal and they have a phase shift of 90 degrees. And you see the current is leading. That means if we have this point here, here is the point where the current is 0 and it rises again, and then it takes the time for 90 degrees until the voltage starts. And this is what we call that the current is leading. And now I said we're talking about steady state AC circuits. And steady state means that everything became sinusoidal. And if we have a look here in the beginning when we switched on our circuit, you see here at the voltage here in the beginning, it's not sinusoidal yet. It takes some time, maybe until here, until we have the pure sinusoidal waves. But when the circuit reached the steady state, then all the currents and all the voltages in the whole circuit are sinusoidal and they have all the same frequency. Now let's have a look at the inductor. Most inductors have a magnetic core and a wire wound around it. And this leads to an inductor with a quite high inductance. We could build an inductor without this magnetic core, then the inductance would be lower. And if you just ignore the windings, just a wire has inductive behavior too. You remember from school that we have magnetic fields around a wire. But the inductance there is quite tiny and we ignore it here. We are talking about the real inductors. Okay, if we have a magnetic material and let's say we have an ideal conductive wire wound around it, then it should behave like a short circuit, shouldn't it? Because we have this ideal wire around it, and where should any resistance come from? Let's begin with a simulation again. I built a small circuit in my simulation program. We have here 2 resistors and an inductor. And here is a DC voltage source, but this voltage will be switched on and off. You see here the voltage is 0 for 2 milliseconds and then it increases to 1 volt, and after 10 milliseconds it's switched off again for 2 milliseconds. Okay, and now you see here we have 2 resistors in parallel to this voltage source, and if an inductor behaves like a short circuit, because we said it's just an ideal wire turned around a magnetic material, but what should it do? So, and that would mean that we should have the voltage drop of 1 volt here at the two resistors, and that would lead to a current of 1 ampere here. And let's have a look what happens in the inductor with the current. What is that? Have a look here. This here is the scale for the current, and the current is 0 in the beginning, and then it smoothly increases until we reach 1 ampere. And when we switch off our circuit, the current does not disappear rapidly, but it smoothly decreases. And then when we switch on the voltage again, the current increases again, but smoothly and not rapidly. And in the end, it reaches the 1 ampere value we expected from it. Okay, and a last thing, I want to display the voltage drop at the inductor. Let's have a look. Holy crap, what happens here? The voltage is 0 in the beginning, then it rapidly increases to 1 volt and decreases slowly, and then when we switch off our source, then the voltage at the inductor is even negative, and the absolute value decreases then. So an inductor definitely does not behave like a short circuit if we look in detail. If we wait long enough and we call that the steady state, then the voltage at the inductor is 0, so it behaves like a short circuit, and the current here in our circuit is the 1 ampere through the inductor, and that is what we expect in a short circuit. But directly after switching on or off our voltage source, we have a transient effect. Okay, let's discuss the element equation. Okay, we have seen that our inductor does not behave like a short circuit. Not in the period of time we call the transient effect. After it behaves like a short circuit. But why? Let's have a look. So we have our inductor here, and let's say a small current begins to flow. Okay, we know that a current produces a magnetic field, and we will find that magnetic field in our magnetic core. Okay, and now an important rule from physics comes, and it's Lenz's law. Maybe you remember it. It says that a changing magnetic field works against its cause. If you want to change a magnetic field, it always tries to suppress the cause of the variation. And an inductor does it by a voltage drop. Again, we had an ideal conductive wire here, but when the current changes, then the magnetic field changes, and that causes a voltage drop. And if the current increases, I indicated with a bigger arrow, then the magnetic field increases, and this still leads to a voltage drop. And as long as the current increases, the magnetic field will increase, and this always leads to a voltage drop. And now we can come to and understand the element equation of an inductor. We have a voltage drop at an inductor when the current changes. And the other way around, if we derive the current by the time, multiply it with the inductance, then it leads us to the voltage drop. Okay, let's discuss our important cases. If we have a steady state current, we've seen it in our simulation. Steady state means that the loading process is over. So we have a DC current here and we want to calculate the voltage drop. We can use our element equation, and this time the current is a constant. And this means that the time derivation becomes 0. And that means that the voltage drop at our inductor is 0. So if we have a steady state DC circuit, and steady state means we switched it on and waited long enough that all the transient effects are over. And if we have such a steady state DC circuit, then an inductor behaves like a short circuit. Let's have a look at the inductor in an AC circuit. An AC circuit means here that our current is sinusoidal. And again, we are talking about steady state sinusoidal circuits, and what steady state means here, we will discuss that in a minute. Okay, we will take our element equation again, and this time our current is sinusoidal. And that means if we do our time derivation here, it leads to a cosinus function, and we already know that we can express a cosinus with a sinus function plus 90 degrees. So this here is the amplitude of our voltage, and if we compare the voltage and the current, we see that they are both sinusoidal, and we have a phase shift of 90 degrees, and this time the voltage is leading. And now let's have a look into our simulation program again. I use the same circuit in our simulation program. So we have here our two resistors and our inductor, but this time I use a sinusoidal voltage source. You see here the amplitude is 1 volt and the frequency is 100 Hertz. And now I want to have a look at the current in our inductor. Okay, and it looks quite sinusoidal. And now I add the graph for the voltage drop at the inductor. Okay, and again it looks quite sinusoidal. I will remove the input voltage, and now we see in red the voltage drop at our inductor, and in blue the current which flows through it. And you see here in the very beginning the current does not look sinusoidal, and we have to wait a bit until we reach our final values. But after a while you see the current and the voltage are both sinusoidal, and we have a phase shift of 90 degrees between them, but this time the voltage is leading. And now let's have a closer look at the transient effects. So the effects in the beginning when we close or open a switch in a circuit. Good news is in this lecture we will only discuss DC circuits, and we will only discuss circuits with only one capacitor in it or one inductor in it. Okay, let's start. We have our circuit here. There is an uncharged capacitor and a resistor and a DC voltage source. In the moment t equals t0, we close this switch. Okay, and now we have a system and we have three unknown variables. We don't know the current, we don't know the voltage drop at the resistor, and we don't know the voltage drop at the capacitor either. Okay, let's have a look how we could solve it. We have three unknowns, and that means we need three equations to solve our problem. We could start with our element equations. We know at a resistor that voltage and current are connected with Ohm's law. And from today, you know the element equation for the capacitor. Okay, we need a third equation, and we use Kirchhoff's voltage law, and it says that the sum of UR and UC equals the source voltage U0. Okay, our three equations with our three unknowns, and now we put them in together. We could express the current of Ohm's law with the element equation of the capacitor. Okay, and then we could use the new equation and change the UR from T with it from our Kirchhoff's voltage law. And this leads to this equation here. Okay, what have we won? Okay, we have an equation where the only time variable is the voltage UC, and we are looking for that, but there's also the time variation. Okay, and there's a constant in front of the time variation, and I can say it now, we call that the time constant tau. And the whole thing is a first linear homogeneous differential equation. Pooh, what could we do with that? I will show you. The good thing is that our problems will always lead to a first order linear differential equation like this. And we will always solve that equation in that order that the function we are looking for stands alone. So in this case, this is the UC from T. And then we have the time derivation of it, and there can be a time variable in front of that. And if we have such an equation of the form tau times the time derivation of the function we are looking for plus the function itself equals a constant, then this leads only to one solution and always the same solution, and this is k1 plus k2. Those are two constants. We have to figure out which values they have. Times e in the power of t minus t0. T0 is the moment where we close or open a switch in our circuit, divided by this time constant tau. Okay, I will show you how we can use it. So we found this differential equation for our system. And now the mathematics tells us that the solution is this equation here. And we have everything but k1 and k2. And we find these two constants with the so-called boundary conditions. And the first boundary condition we use is that we have a look on the voltage at the capacitor when we close the switch and wait a long time. Let's have a look what happens in a mathematical way when we put infinity for our time variable t into the equation. So that means that we have an e function of e in the power of minus infinity. E in the power of minus infinity is 0. That means that our equation is just k1 if we put infinity for our time variable t. Okay, that is the mathematics stuff. And now let's have a look at our circuit. What happens when we close the switch and wait long enough? When we wait long enough, the capacitor will be fully charged, and that means that no current would flow anymore. And that means that we have no voltage drop at our resistor, and according to Kirchhoff's voltage law, UC would be the same as U0. So therefore we found our first constant. Okay, and there's another constant, and therefore we take the other boundary condition, and that is the moment where we closed the switch, so it's t0. Let's have a look at our equation. Here we have e in the power of minus t0. So the exponent is 0 and e in the power of 0 is 1. So that means that our equation is just k1 plus k2. This is mathematics. And now we have a look at our circuit. I said that in the beginning the capacitor was completely uncharged. And that means that the voltage was 0 when the switch was still open. But in the very moment where we close the switch, the voltage at the capacitor can't change its value rapidly, and that means that in the very moment where we close the switch, the voltage at the capacitor is still 0. Okay, so we can solve this equation for K2 and find out that our K2 is minus U0. And therefore we are finished. We have our time function for the voltage at the capacitor. Let's draw the function. So our x-axis is the time and the y-axis is the voltage drop at the capacitor. And we know that if we wait long enough, we will reach the voltage level U0. Okay, and at the moment t0 we close our switch. And therefore we know in the beginning the voltage will be 0, and we know if we just wait long enough the voltage will reach the level U0. And now between these two straight lines we have an exponential function. And yeah, now the question is how we could draw it. It could be that it rises quite quickly or smoothly and slow, and there is our time constant we can use. You remember our time constant in this case was r times c, and we can draw this constant in our graph. So and our time constant has the unit seconds, and we draw there t0 was the moment where we closed the switch, and then we wait the amount of time of tau and draw this time in our graph too. And now I draw a straight line, and this straight line is the asymptote of my exponential function in the beginning. And this straight line begins from the moment t0, it ends at t0 plus tau, and from the y-axis it begins at the initial voltage at the capacitor and ends at the final voltage of the capacitor. And now we can draw our exponential function quite good just with a pen, and yeah, this is the best we could do on a paper. And now I said that this tau, a resistor multiplied with the value of a capacitor, should be a time. Let's have a look on the unit. So tau has the unit of a resistor multiplied with the unit of a capacitor. So we could say that it's volt per ampere multiplied with coulomb per volt. You see, we get rid of the volt and we have here coulomb per ampere. Now remember, ampere was the charge per time, so it's coulomb per second. And now you see we get rid of the coulomb, and really the time constant tau has the unit of seconds. Okay, I know that this looks quite confusing when you see it for the first time. But the good news is this way of solution is always the same. In our next exercise class, I will show you more circuits and we will analyze them all the same way we did it here, and you will see that it's really always the same.